Thank you for your introduction. Yeah, so we go from higher education to primary education and then to vocational education in between, kind of in between. I'm going to tell you something about computer or teacher and about prediction dropout. So it also has a link to the first presentation of this session. I'm Irene Eegdeman. I'm a PhD student at the VU, but I'm also a teacher at a vocational education institute called RC Top. And the students I work with are here in the upper secondary vocational education. So after primary, students get tracked and then go to vocational education. And that's also where I teach at the sports academy. Well, in order to tell you something about computer or teacher, I have to tell you something about both, about predicting students. And before we made a prediction of student dropout based on theory, and we choose variables. So we thought a few variables like GPA, but also attendance might be a predictor of student success. So we put those variables in our model, and we got the output. We got a prediction of student success. Our approach is a little bit different. We use the information we have about students, most information. We know output because we use data from history to make a prediction of the future. And we use machine learning techniques in order to make a prediction of the students who are going to be the next freshman students. And the machine learning algorithm chooses which variables are best to predict student dropout. And now I'm going to tell you something about the invitation of students, because we not only made predictions of student dropout, but when you know these predictions, you can also rank them. And because not every school has all the money and time to spend on everybody, you might have to choose which students to help preventing dropout. So that's why we came up with an invitation rule. And we did that by ranking all the students according to this prediction, and then calculate sensitivity and precision. Well, sensitivity is how much of the dropouts have you targeted, so how much of the students have you seen if you want to invite a certain percentage of students. And precision is how much of those invited students are in fact dropouts. Well, what you can see here is that we have 5 measurements. So we have at the start of the program, after period 1, 2, and 3, and 4. And you can see that how much. So you can see how the sensitivity is getting better in the year. So the random line is like flipping a coin. Someone comes in, you flip a coin, and somebody is dropout or not, and this is the random line if you're right or not. And you can see over here that those are the different machine learning algorithms, and over time these lines are getting steeper and steeper, so our sensitivity is getting better and better. For example, if we invite 100% of all students, we also have 100% of the dropouts in our sample. But after period 2, when we only invite 20% of our students, we already have 50% of all the dropouts in our bubble that we want to target. If it's going, if it's going about precision, then you can see here, if you have invited every student, then approximately 45% of all the students are in fact dropout, because almost half of this sample is dropout. So if you invite every student, yeah, then you have every dropout, but only 45% is the student you want. If we are very strict to ourselves and we want to have 100% dropouts in our sample, then you can see here with these algorithms, by inviting 20% of the students, I have 100% of those 20% of those students are in fact dropped out students later on. So it's about sensitivity and precision. and ranking the students according to a prediction. Over here, you can see it the same thing, but then in a table. If we are very strict to ourselves, so what we want 100% of our targeted students to be a dropout, then after period 1, we go to the first 12%. Then you have 27% of the dropouts in total in percent. So it's a way to show policymakers which students to target for a certain intervention. We didn't even talk about intervention, but only who to target in which period of time. Okay, so if we have talked about the computer, now we go to the teachers. Because when you walk into a teacher's room at the beginning of the year, most of the time, and I do a lot, when I say, well, I'm doing research about student dropout and we're trying to predict student dropout, then they say, well, look no longer, search no longer, just ask us, because we know who is going to drop out. So that's what I did. I asked 9 teachers of the Sport Academy in Amsterdam, who is going to drop out, how certain are you of those dropout prediction, and based on what? And I just compared the two, so I compared the models with the predictions of the teachers in order to see who wins, who is better. Now, what we did was we performed the Kendall-Stau rank correlation. So that means that if the Kendall-Stau is +1, the observations have an identical rank between 2 variables. So the outcome is exactly the same as what the teachers had predicted or the model has predicted. And if the Kendall correlation is 0, then that's the chance level. So that's the flipping a coin. And we compared week 1 predictions with this chance level and also with the models. Yeah, and what you can see over here are the teachers. So I had 3 questionnaires at the start of the program, after period 1, so after 10 weeks, and after 20 weeks again. But you can see the 3rd questionnaire was not really filled out a lot, so that's why we focused on the first 2 periods. And what we can see is that at the start of the program, the teachers can make a pretty good estimation of the at-risk students. I can show that in a figure over here. You can see that the yellow lines are the different teachers, and we also made a teacher mean. So we averaged the prediction of the teachers and made a new ranking of all the students, and that made a pretty good estimation of who's going to drop out, better than our machine learning models. After period 1, you can see that everybody progressed, so the predictions got better, and the models and the teachers really came out quite the same. Here you can see everything in numbers. So you can see we have 1 teacher who was really good at the beginning of the period to have an estimation of who's going to drop out, and we have the random forest. Oh, sorry, over here, who's also has a pretty high Kendall-Stau. But after period 1, all Kendall-Stau's correlation coefficients are about the same. Okay. So what we also did was compare the teacher mean with chance level and with the machine learning algorithms. And what you can see is that the teachers were approximately 60 times more likely that they have a better prediction of dropout than chance level, but also that they were better than one of the machine learning algorithms. After period 1, as the figure also showed, the algorithms took over or were almost the same. But then there's also the question, we have computer versus teacher, but maybe the teachers can also help the computer. They can help the models be better. So is it not only computer versus, but is it also computer with teachers to make the dropout predictions even better? Well, because I've made an estimation of the future and I needed to pass, I could not do all the machine learning algorithms over all the students that we had, because I didn't have a teacher prediction or in the former years. But we could average the predictions of the teacher and the predictions of the model, and rank them again and see if the predictions got better. Now, what you can see, oh, sorry, that's over here. What you can see here is that we have the hunch, that's the teacher mean. We have the random forest, that was the best performing algorithm in first at the start of the program. And if I combine those two, you can see that at the start of the program, the sensitivity is higher when I combine the two, and the precision after a while gets higher as well. So you can see that if by combining the two models, so by combining the teacher and the models, we can even have better results than before. I forgot to show you this graph, because I started with the amputation rule about the sensitivity and precision at the start of the program, and after period 1, here you can see that the hunch of teachers is really higher, especially for the precision part, than the algorithms. So in this case, it was about 100 students. The first 6 students that the teachers labeled as dropout were in fact after year also dropout. So they had a really high they predicted really well about these first students. And after period 1, you can see that also the algorithms made a really good estimation in the beginning. So that brings us to the conclusions. Some teachers are capable of making accurate predictions. Other teachers a little bit less accurate. But if you combine these predictions and see it as the wisdom of the crowd, and make a ranking according to the common view of the teachers, then at the start of the program, these predictions are pretty good, and they can also help make the models at the start of the program better. That makes us, of course, curious about the next step, because we now only know who we want to help. We have to target if we have an intervention, but the next step will also be what to do. So the next step would be that I want to implement the invitation rule at different vocational educational programs. So not only in sports, but also in all the other sectors you have, and combine that with an intervention study, so that the students who are targeted also can be helped and hopefully have a positive influence in dropout, or maybe let students switch earlier. And we want to do that in the so-called practoraat. It's like a research group, but then in vocational education. So hopefully in the next coming weeks, I can keep you posted on this project. And hopefully we will be a little bit closer to really get a grip on preventing dropout. So that was in a nutshell what I had to tell you, and I want to thank you for your attention.